Welcome to Online Algebra 2. Tonight, we are going to cover section 7-5, exponential and logarithmic equations. So our objective here is to solve these exponential and logarithmic equations. And what you really need to understand is that there's a couple different techniques that you can use depending on if the equation is an exponential equation, and depending if you can make them have the same bases or you can't, or if you have a logarithmic equation and they have the same base or they don't, okay? And what we're gonna learn is that we can use properties to solve it, or we can use logarithms to solve exponential equations and exponents to solve logarithmic equations since they are inverses of each other, okay? So what is an exponential equation? So any equation of the form b to the c to the x power, like that, where the exponent includes a variable, is an exponential equation. This, right, is not, whatever, that is not an exponential equation because the variable is not in the exponent. This is an exponential equation because the variable is in the exponent, okay? So what you're going to want to do first is you're going to want to look at the problem and ask yourself, is it possible to solve this by making them both have the same base, okay? Is there a way to make 16 and 8 both the same base raised to a power? And yeah, we can make both of these a power of 2. 2, 4, 8, 16. 2 to the fourth power is 16. And then don't forget this stays there, right? Power to a power means multiply the exponents together. And then 2 to the third power is 8, okay? Now, the power property of exponents says that if you have the same base, the exponents must be equal to each other, okay? So think about that. This is 2 to the third power. In order for these two sides to be equal, this has to be 2 to the third power as well. Well, but it's 12x. Okay, so we just divide out the 12, and we get that x must be a quarter, right? And now if you plug that in, x is equal to a quarter. If you plug in x, you get that these two are both 3, okay? That is a property that works no matter what, as long as you can make both bases exactly the same, okay? And when you can do that, the exponents must be equal to each other. Technically, you can take the logarithm of both sides and move the exponent over, which is what we'll do next, but this is a little bit easier, okay? So look at this problem. Is it possible to make 27 and 81 both the same base raised to some exponent? Well, 3 to the third power is 27. 3x stays right there in the exponent. And 3 to the fourth power is 81. Multiply these together, power to a power, and multiply exponents. 9x is equal to 4. So x is 4 over 9. Okay? If the bases are the same, the exponents must be equal to each other. Okay? Now, what happens if the bases are not the same? Because they're not always going to be the same. You can solve an exponential equation by taking the logarithm of each side. So if m and n are positive, right, and m is equal to n, then the log of m is equal to the log of n. Okay, so it doesn't matter what these two things are, as long as you take the same base logarithm, in this case you don't see it, it's a base 10, as long as you take the same base logarithm of each side, That's the same thing as like adding something to both sides, multiplying something to both sides. As long as you do the same thing to both sides, the equation is still going to be equal to each other. Okay. So take this equation. There is no way to make 15 and 285 the same base. 15 squared, 15 squared is 225, and 15 to the third is going to be much bigger, 3375. Okay, so 285 is not one of these two numbers. Okay, so it's not possible to make these two into the same number. So we're going to need a different technique. This is not going to work. All right, and the technique is to just take the logarithm of both sides. Now, you can take any base logarithm you want as long as they're both the same. I chose base 10 because I didn't write it down. The reason why you choose log base 10, or the logarithm that we're going to talk about in the next section, natural log, the reason why you choose one of those is because that is what is on most calculators, right? So you could pick anything and use the change of base formula to calculate it on your calculator, or maybe your calculator has a button like that where you can do any logarithm you want, but just to be safe, put the logarithm that's on every calculator, base 10. All right. Then we're going to take this exponent and we're going to use the power property to move it to the front. Now we're going to divide everything. This is all one multiplication. Divide it out. And they cancel each other and leave you with x by itself. If I do that to one side, I have to do it to the other. And so my answer is whatever this turns out to be when I put it in a calculator. So my answer, if I write it as a logarithm, 285 over 3 log 15, that is an answer. It's an exact answer. Plugging this into my calculator, you should get log of 285 divided by 3 log 15. You should get 0.6958. And usually we round this to about 4 decimal points is usually pretty standard for logarithms. Okay, because a little bit of a decimal can could really change your answer. Let's try it again. 5 and 130. I can't make them have the same base because 5 squared is 125. It's not 30. Okay, so that means that in order to solve this, okay, I am going to take the log of both sides of the equation. Power property moves that to the front. Log of 130. Now I could turn this to a decimal now, but I'd rather leave it until the very last step in order to be as accurate as possible. 2's cancel out, logs 5's cancel out, and so I'm left with x is equal to the log of 130 over 2 log 5. Okay, now you're going to need a calculator. There's no real way to do this without one, so just make sure you have a calculator that can do basic logarithms, which you should have one, and you get 1.5122. Okay, so again, same base. This is easier. If you wanted to, you could take the log of both sides and still get the same answer, same technique. 3x log 16 is equal to the log of 8. Divide out the 3 log 16. And x, plugging this to a calculator, you're still going to get 0.25 or 1/4 if your calculator spits out a decimal. Okay, so This technique works no matter what, right? You have an exponential equation, you can take the logarithm of both sides, all right? This is just a little bit faster, and you don't need a calculator for it. Okay? So, next, let's try a question solving an exponential equation with different bases again, a little bit harder because notice now we have two variables. We have a variable on both sides. Okay, so our technique is still going to be the same. We're going to have to take the log of both sides. Okay, using that power property, the exponents move to the front of the logarithm. So we have the whole exponent in parentheses, log 2, the whole exponent in parentheses times the log of 3. Okay, now my goal is to collect all the x's, to get all the x's together. All right, in order to do that, I'm going to have to distribute this. So I'm going to have to multiply these both like this. So that's x log 2 plus 3 log 2. Because I can't put the x and the 3 together. I can't put the 2x and the 5 together. So that's 2x log 3 plus 5 log 3. Okay, in order to get all the x's together, I'm going to put them all on the same side. So I'm just going to subtract this whole term from both sides. So that's x log 2 minus 2x log 3. And I'm going to subtract this from both sides because that's a 5 log 3 minus 3 log 2. I'm going to subtract it. I'm going to get it out of there because it doesn't have an x. Now, if these were the same, log 2 and a log 2, I could put them together, but they're not. So the only thing I can do is factor out a common term. And the common term they have is x. So that's log 2 minus 2 log 3. Now I have a multiplication. This side stays the same. I have a multiplication. I just divide this out. It cancels. And now I have my answer. So x is going to be equal to 5 log 3 minus 3 log 2 over the log of 2 minus 2 times the log of 3. Now, unfortunately, plugging this into a calculator can be a bit of a challenge if your calculator is not that good. So just be careful when you do it. 3 log 2 over the log of 2 minus 2 log 3. Luckily, my calculator here lets me put it in all one term looking just like this. If yours doesn't, you might have to do this minus this, then divided by, and in parentheses, this minus this. Okay, so just be careful. And you should get negative 2.2696. Okay, so to recap this problem, because it's a little bit longer, is realize you can't make the 2 and the 3 the same. So take the logarithm of both sides, move the exponents to the front, distribute, collect the x's on one side, factor it out, and divide what's left out so x is by itself. Right? And then calculator for the answer. All right, let's do a word problem. Okay? So, wood is a sustainable, renewable, natural resource when you manage forests properly. Your lumber company has 1.2 million trees. You plan to harvest 7% of the trees each year. How many years will it take to harvest half of the trees? Okay, so if you are harvesting 7%, that means that you are taking that away. So this is a negative growth. Makes sense. You're going from 1.2 million down to 600,000, right? Half. So you're trying to see how long it's going to take to burn through half of the trees. So notice our growth rate is negative. Our formula for this is going to be my standard exponential formula, right? It's going to be some function of time in this case. It's going to be equal to the starting amount, a sub 0, times 1 plus the rate to the t power. Okay, so here's my finishing amount. We can even call this a final. Okay, so it's going to be 1,200,000 is getting, no, sorry. Whoops. It's going to be 600,000 because it says how many years will it take to harvest half, right? So that's my final amount. My starting amount is 1.2 million. 1 plus what's my growth rate? My rate is a negative 0.07. Okay? Because you're taking away 7% of the trees. And if you look at this, that means there's going to be 93% left. Makes sense. Okay, and there's my exponent. There's my variable. How long, right? That was the question. How many years? Okay. So, first step is we can simplify the parentheses and divide out the 1.2 million. And we just get 1/2, right? 600,000, right? So this is 1/2 is equal to, let's simplify this. That gives me 0.93 to the t power. Unfortunately, I don't really think there's a good way to turn 1/2 and 0.93 into the same base. So take the logarithm of both sides. Then use the exponential property to bring that exponent to the front. So that's t times the log of 0.93. And then the log of 0.93 is just a number. Divide it out. Okay? And so all that's left is t by itself. These two cancel. And my answer is whatever the log of 1/2 divided by the log of 0.93 is on your calculator. And we should get 9.55 years, approximately. Okay. So, you know, you can make that into a 10 or just use that. Let's do logarithmic equations. So logarithmic equations are the opposite of exponential. Those are all exponential equations, right? The variable is in the exponent, right? All of these, the variables in the exponent. So logarithmic equations is an equation that includes a logarithm. Very, very complicated definition here. This is an equation that includes a logarithm. And it's even easier to solve than the other one that had the same base. You got a logarithm on both sides. If you have a logarithm on both sides and they have the same base, the insides must be equal to each other. So this just turns into 5n minus 10 is equal to 3n plus 4. And now you just have a linear equation. So that's 2n, add 10 to both sides. So n is 7, okay? And that's it. If these two are different, you can't do this problem, okay? So if you have a situation like this, we have a logarithm equal to another logarithm, it is very straightforward to solve this if those two logarithms have the same base. You could try to make them change one base to another base, but that's a little more past the scope of this course. If you have a logarithm equal to a number, now that's different. Okay, so if you have a logarithm equal to some number, you change it to an exponential equation. Remember how logarithms work, okay? Is that I take this logarithmic expression and I can rewrite it with a base of 10. 2 is the exponent, and it's equal to the stuff inside the logarithm. So 100 is equal to 4x minus 3. And there we go. Another linear equation to solve. 103, 4x, just divide out, and we have that x is equal to 103 over 4, which is, if we want to turn it to a decimal, 25.75. Okay. Logarithm equal to a number, you change it to an exponential expression. Logarithm equal to a number, change it to an exponential expression. Don't forget what this means. That is a fraction. Okay, now probably everybody's freaking out because now we have a fraction. That's okay. Common denominator, so that makes it 29 over negative 29 over 10 is equal to negative 2x. Divide everything by negative 2. That's multiplied by negative 1/2. And we get that x is equal to positive 29, whoops, positive 29 over 20. Not so bad. Okay. Let's just double check this. Yeah, got it. Okay. Now, if you have two logarithms equal to a number, you have to combine them first. So you can't actually solve this the way it is. We have to actually use the properties that we learned in the last section and put these two logarithms together into one, and then do this. Okay, so I see a plus. That means that these two logarithms combine with multiplication. Okay, and so this turns into the log of x squared minus 3x is equal to 1. I don't see a base. That means the base is 10. So it's 10 to the first power is equal to x squared minus 3x. I now have a quadratic, which means the best idea is to set it equal to 0 and use the zero product property in order to factor this. And it factors to x minus 5, x plus 2. Factoring doesn't go away, right? It's still how we're going to solve some of our problems. So x is equal to 5 and x is equal to negative 2. However, when you have a situation like this, in fact, in all these that have more than one variable, you should be double checking your answers, because hopefully you remember that we are not allowed to take the logarithm of a negative number. So that means that one is out, okay? Because if I plug negative 2 in there, I would get a negative number. If I plug negative 2 in there, I would get a negative number as well, right? You can use x could be equal to a negative number, but the inside of a logarithm cannot, okay? So we get rid of that. The answer is 5. And if you plug that into a calculator, you would see that it does indeed work. Let's try again. Let's try our got it problem. Minus means that we're going to put the logarithms together with division. So it's 6 over 3x is equal to negative 2. So now the base is 10 to the negative 2 power is going to be equal to the inside of the logarithm. 1 over 100 is equal to 6 over 3x. I can cross multiply that and say 3x is equal to 600, divide out the 3, and we get that x is equal to 200. Much easier because we didn't actually get a quadratic expression. Okay, so the answer here is 200. Does that make sense? Yes, because when I plug that in there, I get a positive number. That's all we're looking for, is that the inside of the logarithm must be a positive number. Okay, so solve each equation. They can both be turned into a base of 3. Take the logarithm of both sides. This is 10 squared is equal to 4x. And this is 10 to the third is equal to x over 2. Okay? Be very careful. Put these two together with either a multiplication or division. Error, what's the error here? Is that you cannot say this, right? See, look, we have a log of 2 on this side, a log of 3 on this side, right? We cannot relate these two to each other. So this is not solvable the way it is. Okay? Is it possible for an exponential equation to have no solutions? Sure, an exponential equation can have no solutions, right? It could be something that is undefined, right? And so that is 7-5 exponential and logarithmic equations.